Alright, hey everybody. I want to just take a few minutes to go over one of the questions that was on the homework, and I noticed a lot of you were really struggling with this one because you were using exactly the same method that we used in class, but this situation is slightly different, and so we have to treat it differently. And so I wanted to just take a few minutes to go over exactly how to do this. So the situation is you put a cube of ice in a hot water bath. This water is about 35 degrees Celsius. That's pretty close to like 95 degrees Fahrenheit, so it's pretty warm. The ice is below freezing temperature. It starts at negative 25 degrees Celsius. So there's a few things that need to happen here. Notice that the ice cube is much smaller than the bath of water. So the ice cube is going to melt, and that is because we actually have heat going from the hot water bath to the ice cube. So in other words, there's energy being transferred thermally from the water to the ice cube, and therefore melting the ice cube, and then the ice cube will become water itself, and the two will mix together, thus lowering the temperature of the water and the ice bath. So we expect that the final temperature of this pot of water will be probably just slightly under this initial water temperature of 35 degrees, because the ice cube is going to bring down the temperature a little bit, but not a lot. So what's got to happen in order for this to happen? Now, I've already gone ahead and written down all of our givens for this problem. You've got masses, you've got initial temperatures, and then you have specific heats, as well as the heat of fusion. So now that seems to be all of the relevant information that we might need. So let's actually think about what's going on. So let me take a moment over here to sidestep. We've got two different things that happen when you transfer heat or you transfer energy thermally. So here it is. So this is what we've got going on. Let me actually draw this even bigger. So I'm going to go ahead and do this. All right. I'm going to put temperature here on my horizontal axis and the energy that I'm inputting thermally on my horizontal axis. And so let's watch what happens. So this ice is starting at negative 25 degrees Celsius. That's well below its freezing point. So it's really, really frozen. It's solid ice at this stage. So when we start inputting energy thermally, what's happening is initially its temperature is going to increase. So its temperature is going to increase. The way it does that, and it stays ice at this stage, and the way that we're going to determine how much energy we need to put into it to raise it up to its freezing point is using Q equals mc delta T. So that's what we're going to use for this stage. But there's actually three processes that take place. The first one is that the ice has to come up to zero. Then once it's at zero, then it's going to start breaking up those bonds. Because what's happening is you've got a solid structure of ice. You have a crystalline structure like this with all of these different bonds. And those bonds, you literally need to take energy in order to break them up. So you're going to break each of these bonds, and that takes energy. That energy is given by what we call the heat of fusion. So during this stage, you're going to have a combination, kind of a slushy, of ice and water. So this is ice plus water. And at this stage, we're going to use that Q equals ml equation. Now here, because we're going from solid to liquid, we're going to use Q equals mlf, the latent heat of fusion. All right, great. So there that is. So now we've got just water. At the end of this stage, we have just water at 0 degrees. But we know it's got to come up further, right? We expect that final temperature of that water that originated as ice cubes to get pretty close to 35 degrees Celsius. Probably not exactly, but it's definitely going to increase in temperature further. And at this stage, we're going to have just plain water. And since we're increasing the temperature again, this is going to be Q equals mc delta T. Again, so we have three different stages. So what's happening when the energy being transferred thermally from the hot water bath to the ice cube, that goes into three different processes. That goes into first increasing the temperature of the ice cube, then changing the ice into water, then increasing the temperature of that water that was initially the ice cube. Okay, great. So there we go. So we've got something good to start with. It's okay. I'm going to erase these givens. The next piece that we know, and we saw this in class, and this is no different than what we would have normally, is that the energy that is gained by the ice is negative the energy lost by the water. In other words, this Q has to go from the hot water to the ice. That's the only way we can make this work. So the energy gained by the ice, like we said, this goes into 3 different processes. So we have to split this term up into 3 separate terms. So the first term is going to be the Q that it takes to increase the temperature from -25 to 0. So that's the first term. That's this part of our slope right here. Then we have to put in energy to break up those bonds. So now we're going to do the Q for it to go from solid to liquid. We usually just call that latent heat of fusion. And then I've got another term here, and it's going to be the term that brings the temperature of what it was originally ice up to, it's going to be close to that 35 degrees, but not exactly. So Q increase T from 0 to TF. And that has to equal the energy lost by the water. Now all the water's doing, the water's not losing so much energy, so much thermal energy that it's turning into ice or anything like that. It's only losing a little bit. It's just going to drop in temperature. So here, this is going to be the Q that decreases the temperature from 35 to whatever this TF is. And I don't know what that is. We're trying to figure out what that TF is. Okay, so let's take this one more step. Here I'm going to use MC delta T. Here I'm going to use MLF. And here I'm going to use MC delta T again. And this has to equal, oh, and I forgot my negative sign, my all-important negative sign right here. And so this is also going to be an MC delta T. Now, we have to be careful. I need to put some subscripts on these because these are not all the same MC delta T's, and we don't want to get ourselves mixed up here. So over here, we're dealing with the mass of the ice. That was just that 6 grams that we started off with. Here, we've still got ice, so this is going to be the specific heat of ice. And our delta T, in fact, I'm actually going to erase that delta T, and I'm going to write it as T final minus T initial. T final is 0 minus T initial, which was -25. And we're okay to do this in Celsius because we're dealing with differences in temperature as opposed to just straight up temperatures. Then we've got the mass of the ice again times the latent heat of fusion for water, going from water to ice. So I've got that, so this is looking good. Sorry, this is MI, I was calling it M-ice, I think, so we'll be consistent there. Let me just move this over a little bit. M-ice times C. Now I'm actually increasing the temperature of water. So now I want to use specific heat of water, not specific heat of ice. Because now I'm raising, right now it's all water, and I'm increasing the temperature of that water. So I've got that 6 grams that was initially ice, it's now water, I'm increasing the temperature of that. And again, I'm going to replace this delta T here with TF, that's the mystery thing that I'm looking for, minus its initial, which was 0 for just that step, 0 degrees Celsius. And then this is going to equal the mass of the water times C of the water times this delta T of the water, I'm just making myself a little bit of room, TF minus, and its initial temperature was 35. So just TF minus TF. Nothing too fancy going on here. Now, at this stage, it's just a matter of plugging in all of these numbers. We literally have all of the numbers except for TF at this stage. And so, let me see here if I can just do this quickly. The mass of the ice is 6 grams, which is 0.006 kilograms. I do have to be careful about that. CI here is 2090. 0 minus -25 gives me 25. The mass of the ice here again, 0.006. The latent heat of fusion for water to ice is 334,000, because it's kilojoules. Let's see, I'm going to track this onto the next line here, if that's okay, just because I'm running out of room. Mass of the ice again, this is going to be 0.006. Now let's C of water. C of water is 4186 times TF. And this has to equal the mass, negative the mass of the water, which was half a kilogram in this case. Half a kilogram times C of water, which was 4186, times TF minus 35. And now I hope it's really clear. We literally have all numbers except for TF. And so now it's just a matter of figuring out what this number is, figuring out what that number is, and adding them. Then figuring out what this product is. So you're going to have some number plus another number times t. And then over here, you're going to get the same type of thing. Just take whatever this number is here, and then you're going to distribute it in to the TF and the 35. At that point, you just bring over all the terms with TFs to one side, all the terms with just numbers to the other side, and solve for TF. And you should find, what I got was that my TF is about 33.49 degrees. It did not drop considerably, but it did drop a little bit, which is pretty much exactly what we expected. Now, some of you did basically just this step on your homework. You used MC delta T equals negative MC delta T from ice to water. But again, we're missing this all-important step with this latent heat of fusion, and we're missing the fact that we have two different specific heats. We have a specific heat of ice here and a specific heat of water here, two different specific heats. So you're going to have two different values for these steps. So what ends up happening in your homework problem is that those two mistakes almost perfectly cancel each other out. But on a test, we're looking for how you got to that answer, not just that specific answer. So even though you got really close to the right numerical value, the approach that you used isn't right, and that's what we're looking for on this free response. So I want to make sure that you're clear about this. Again, just a quick recap. You've got 3 different stages for that ice to go through. First, it's got to come up to 0 degrees, then it's got to melt, then it's got to increase temperature again. So 3 different steps. So the energy that's lost by the water when it's gained by the ice goes into these 3 stages, increasing the temperature, going from solid to liquid, and then increasing the temperature again. Here, you're using the specific heat of ice because it was still in the ice stage. Here you're using the specific heat of water, because now it's in the water stage, now it's melted. And at that point, then it's just some ugly math, but you can eventually suss out what exactly TF is. And it's usually a good idea to give them back the answer in the units that they gave you, but if you gave this in answers of in units of Kelvin, that would be okay too. All right, good luck!